Good morning, good afternoon, dear colleagues. It's a pleasure to introduce the talk of my former advisor, Professor San Martin from Unicamp, University of Campinas, Brazil. San Martin needs no introduction. Everyone here knows its important contribution to lithium and application, as well as his impressive contribution to form a research group in this area in the South America, in special. After all, he has supervised around 30 PhD students or more, in addition to the supervision of several postdoctoral projects in the South America. Author of a large number of scientific papers and important books on Lie groups and Lie algebra, and editor of scientific journal. So the title of his talk is B-Convex sets in flag manifolds and maximal semigroup. So please, San Martin.
Okay, thank you, Alexandre. Let me try to talk in this very strange, way, and also let me try to speak in broken English because I am closed in here, and so it's quite difficult. Um, I decided to talk about this B-convex sets on flag manifolds, which is well, it's a theory of convexity of subsets of flag manifolds, real or complex flag. I forgot to say. Well, good morning for everybody. Oh, thank you for coming to this meeting that now is in its 70th edition, and uh, well, and thank you for the organizers, people from Juiz de Fora. Yes, yeah, but who else? Well, I think people from Minas Gerais also collaborate with this organization. Here is, I see Luciana and Nate from the Berlandia. And, well, anyway, thank you for this close to 100 people that is now on the screen. As I was saying, I am talking a subject that started with i- with the development of semigroup theory in semi-simple Lie groups. I did this 20 years ago, and I never returned until now. That now I am a writing a book on semigroups, a monography that will join several results on the subject, semigroups and semi-simple Lie groups. And then when I arrived at the chapter of maximal semigroups of these B-convex sets, I saw that there are many things to develop the theory. Uh, 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 that are still many things to develop in the theory. So I found it nice to talk about this. Although I am aware that not everybody in this meeting is interested in semigroups and or control theory. Anyway, let me say what is this. I prepared some transparencies here, but well, a file uh, with some items that I will talk, and then there are several other files that I will call at the time. Well, what are B-convex sets? So it's a convexity theory. I will say what I understand by convexity theory soon. Well, it's a theory of subsets of a general set satisfying certain properties, uh, I am not interested in do the axioms in detail, but that was developed to understand maximal semigroups in non-compact semi-simple Lie groups. Maximality by the order of inclusion. And here I must say that not every semigroup comes into the scene here, only those that semigroups that have non-empty interior. All this theory of semigroups I have been working with are for semigroups with interior points in non-compact semi-simple Lie groups. I repeat, real or complex groups. This was published, as I said, 20 years ago, and I am returning now to it because I'm writing a book on semigroups, and this is one of the chapters of the book. And there are some results to be proved here, which I put here as problems, new problems to be solved. What are these B-convex sets? Well, roughly, B-convex sets are subsets of flag manifolds, and flag manifolds here are any flag manifold of a non-compact semi-simple Lie group, real or complex, and the flag manifolds are not only the maximal one, but the partial flag manifolds come in also, like a G for SL for the linear group SL linear are the manifolds of flags of subspaces, or for the symplectic group are manifolds of flag of isotropic subspaces and so on. And there are several realizations. Well, these B-convex sets are subsets of these flag manifolds in this general theory, and roughly they are subsets that are the intersection of the cells that contain it. The idea is similar. Let's think, for instance, of a cone in a vector space. It's the intersection of half spaces that contain it, a convex cone. And the idea is similar. Here I look only at open Brouwer cells that are open and dense subsets of the flag manifolds that are diffeomorphic through Euclidean spaces. And the idea is that a semigroup is to be maximal if it is the semigroup, what's called a compression semigroup, semigroup that lives invariant such subset. A semigroup S lives inside the group acts on the flag manifold, and I look the subset of those elements of the group that maps the set C, I'm calling this C, into C. So the semigroup is maximal. One of the theorems is that the semigroup is maximal if and only if C is a B-convex set. I will define what B-convex set. The idea comes from the theory of a semigroup, is that a proper semigroup, again, I put here some group with non-empty interior of the non-compact Lie group. Then, well, in any flag manifold, it lives invariant some subset. You can prove that if a semigroup act transitively on a flag manifold, then it is the Woolley group. So if the semigroup is proper, then it lives invariant, proper subset, compact, closed subset of the flag manifold, and since the semigroup has no empty interior, the semi happens to this subset. In the theory, this is called the invariant control set, The term control set comes from control theory, and it's a subset where the semigroup is transitive inside the subset. It can be proved that in any flag manifold there is just one of these subsets, and the basic defining property of this subset is that, well, the semigroup is transitive inside it. In flag manifolds, there is a unique such subset for semigroups with non-empty interior. And the idea, continuing the idea, to say that the subset is invariant by the semigroup means that the semigroup is contained in the compression semigroup of the subset. So for any semigroup, any semigroup is contained in such a compression semigroup. So very simple idea, if S is maximal, then it must be a compression semigroup of a subset of a compact subset of a flag manifold. So the problem that comes is that what are the subsets such that the compression semigroup is in fact a maximal semigroup? Which subset, which is the class of subsets that really define maximal semigroups. So the key word to looking at this is to select some flag manifolds, and for a special semigroup, for a specific semigroup, one select a special flag manifold that is called the flag type of the semigroup. So this concept of flag type of semigroup comes from the theory of semigroup actions on flag manifolds, and it's the key idea that that is used here to think of this convexity theory. I think I have selected from this. This is part of the book I am writing about flag type. There are theorems like this one, this 319 here, that if you take a semigroup in a non-compact semi-simple Lie group, then it lives invariant. It has a unique invariant control set on any flag manifold. So one of the definitions of the flag type of the semigroup is that it's the unique flag manifold that is maximal with the property that the invariant control set is contractible in the flag manifold. Here, contractible is not does not have the same meaning as in homotopy, although it's connected. It holds this way. Contractible means that element that it's contained in an open Brouwer cell. So it's contained in a subset which is open and dense and diffeomorphic to an Euclidean space. And more than that, there are elements of G, the so-called regular real elements of G, that lives in the interior of the semigroup, that when you iterate the action of these elements, it takes this set shrinks to just one point. So contractible is in this sense. So this kind of a theorem characterizes what is the flag type of a semigroup. There is just one flag manifold which is maximal with this property. It's not unique. It's not the flag manifolds with this property is not unique, because if this happens in one flag manifold, then it will happen in flag manifolds that are below this flag one. There is just one which is maximal. Okay, think, for instance, of the Jordan form of a matrix. The Jordan form of a matrix select a, a pattern of the composition of the matrix into upper triangular matrix. If you take the eigenvalues, the real part of the eigenvalues, and bunch them in just one block, then the partition of the blocks defines a flag of the vector space. And this flag manifold can be called the flag type of the matrix given by the Jordan block. Something similar happens here. The same kind of, well, the flag is a fixed point for the matrix, and something like this happened here for the flag for semigroups. So this kind of theorem is so let's say an enlargement of um, of of the Jordan form of the matrices. All right, muito bem. Vamos lá. Let me start talking about the open cells, which are the basic uh, the basic technical tools. So first, some notation. People that work with me are used the notation that I use always. Start with a non-compact semi-simple group. The basic decomposition is Iwasawa decomposition into compact vector and nilpotent groups, the corresponding Lie algebra decomposition. I write, contrary to Helgason, I write simple system of roots as sigma, because sigma is for S, and the flag manifolds are defined by subsets of the simple system of roots, and as the cosette space, compact homogeneous spaces, compact cosette spaces, and the open Brouwer cells. I take it, well, the set of all open Brouwer cells, I look at this, are the orbits of the conjugates of this nilpotent component of the Iwasawa decomposition. These are open and dense subsets, and as we change the subgroup, we get different open Brouwer cells. For instance, I write here the example. In the projective space, the sets are the sets in the projective space that corresponds to half spaces in the vector space. So they are the lines that are not contained in a subspace in the projective space. This set of Brouwer cells, this is the basic remark here. This set of Brouwer cells is the group G acts on the set of Brouwer cells, and this set is a homogeneous spaces of G, which is also a flag manifold. I call this the dual flag manifold of the given flag manifold, which is defined algebraically by a dual subset, which in turn is given by this expression here, which is W naught is the unique element of the value group that maps the positive roots into the negative ones, the positive chamber into the negative ones. And I call this the principal evolution. This is not usual, but this is a terminology I have been using. And the negative of it maps the simple system of roots into itself. And the set of Brouwer cells is in bijection with this flag manifold. This is a remark that I use quite often. And there are some examples of flag manifold that every maximal flag manifold is self-dual, because it's defined by the empty set. And most of the flag manifolds are self-dual, because this W naught, in most of the cases, is this minus W naught, most of the cases, the identity for most of the Lie algebras. So I wrote here, which are these Lie algebras, the A1BL simple Lie algebras, A1BL simple Dinkin diagrams, um, A1BL, DL, etc. It's listed here. And for most, the flag manifolds are self-dual. Concrete examples are for the projective space. As I mentioned above, a Broussard cell is defined by a hyperplane, so the dual of the projective space is the Grassmannian of hyperplanes. More generally, maybe I return to this, the dual of Grassmannian of k-dimensional subspaces is the Grassmannian of d minus k dimensional subspaces. What's a way of parametrizing, right, the the open Brussels is by looking at the action of G, on the Cartesian product of a flag manifold by its dual. So this is called the diagonal action, which acts, you apply G on both coordinates, on both components, and the orbits for this action is not transitive, and the orbits are parameterized by the Weyl group, or a coset of the Weyl group. In the maximal flag manifold, it's exactly the Weyl group, and the orbits are given by these the orbits of these origins, the origins of the flag manifold itself, and this translation by W. And there is just one open orbit, open and dense orbit, which is given by W, that is the principal involution. This is an open and dense orbit in the product, and is the only open orbit. And this open orbit is used to parameterize the open cells in the flag manifold. More recently, I proved that this open orbit is diffeomorphic to the tangent, and hence the cotangent space of the flag manifold. It's the fibers, this open orbit projects into the flag manifold, and the fibers are diffeomorphic to the open orbit, and hence to the tangent space of each point. And I say that two elements in the flag and its dual, they are transversal if the pair belongs to the open orbit. There are some algebraic characterization of transversality, and here I put one, which is the transversality, transversality itself of the parabolic subalgebra that defines the point of in one flag manifold, and the new radical of the parabolic subalgebra of the other point. So more relevant that this kind of the intersection of the two parabolic subalgebras that define the elements in the flag manifolds is minimal. And minimal means that it's a let's say, split subalgebra with M plus A in In some cases, it's just A. So the open cells become parameterized by the dual flag manifolds by this expression. Uh, to get an open cell in a flag manifold, you go to a point at the dual, uh, look at the fiber uh, of the projection and intersect it with the open orbit, and then project it down to the flag manifold. This gives us an open and dense subset. This is a very convenient way to write the Brua cells, open Brua cells. The other Brua cells, kind of Brua cells, can be written this way also by taking the other orbits. Here I'm concerned only with the open orbits because I'm looking at the B-Convex sets. So I put some examples here. I will go a bit faster. Example, let's say the 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 projective line itself dual, and the product, the Cartesian product, is the torus. And in this case, there are only two orbits, which is the diagonal of the circle and the complement, its complement. And 2 points are transversal if and only if they are not the same straight line. And so the open orbit is the complement of just 1 point. Well, I think I went no, uh, went too fast here. Another example I wrote here, the Grassmannians, when projective and Grassmannians, um, that we can look the orbits, the orbit in the product of two Grassmannians can be seen by intersection, the dimension of the intersection between the subspaces. And okay, let me go to the B-convex sets now, and I am a bit lost with this here. I found. So formally, the B-convex sets, to define the convexity theory, I start with a dual, a definition of the dual set of a set of in the flag manifold. And I define the dual of the set as the subset of elements in the dual flag manifold that are transversal to these elements. For instance, I wrote here the example below. In the projective space, the dual of a subset is the set of all hyperplanes that do not contain any element of the any line in the subset of the projective space. Here is an equivalent definition. It's very nice. I realized this definition only recently, and permits you to extend the notion of B-convex sets. I will talk about this later. The dual of a subset is uh, is the largest subset that the Cartesian product is contained in the open orbit. This is a nice observation, a nice remark that is useful to think about it, to work a technical to work with these B-convex sets. There are some basic properties of this that are that form a convexity theory. First, a subset is contained in its bidual. C is contained in C star star. Of course, C star star, the dual of a flag, the dual of a flag manifold is the flag manifold itself. So the term dual is well posed. Duality is a decreasing map, and there are some topological properties like if the dual of a compact set. I wrote here admissible, a subset. This is for doing semigroups. A subset is called admissible if its dual is not empty. This means that the subset is contained in some open Brouwer cell. The dual of a compact set of a closed set is open, and on the contrary, the dual of um, um, the dual of an open set is closed. Under some details here that must be taken care. Well, finally, the convex hull of a subset it's bidual. Uh, and a set is called B-convex. It is coincides which is bidual. The bidual of C is the set. Well, the dual of C is the set of uh, of um, of open Brouwer cells that contain the set. So to say that it is equal to the bidual or its bidual means that it is the intersection of the open Brouwer cells that contain the subset. I wrote here some basic properties that are essentially the axioms of a convexity theory. Uh, these are some people axiomatize what should be a convexity theory. I don't have here the reference, but I have in some paper that are five. It's like a subset C is contained in its convex hull. Um, uh, a subset C, this subset C is convex if it's the dual of some subset. So this is a good way to define B-convex sets. You start with an arbitrary subset in the in the dual flag manifold and take its dual. Then you get a B-convex set. And there's some topological properties, the convex closure of the convex hull of a subset contains the subset and is compact, etc. Usually, B-convex sets may be quite wild. An example of this is like in, in the projective space, and actually it holds in any rank one group, is that any subset is B-convex. This is because an open Brouwer cell is the complement of a singleton, of a just one point set. So any subset is B-convex. It's quite arbitrary. B-convex sets may be quite arbitrary. I gave an example here that are classes of B-convex sets that are not so arbitrary, are not so wild. The case of in this picture here, a case the set is connected in projective line, then it's associated to a convex cone in the plane. So these are not wild subset, but are quite well behaved subset. So put further property, you get some good um, some restricted class of subset, although B convex may be wide. I have another example here in projective space, B convex sets that are defined by convex cones. If you take a convex cone in the vector space and see the corresponding set in projective space, real vector space, see the corresponding set in projective space, then it's a B-convex set. This comes directly from the definition and the remark what are the open Brouwer cells in projective space. I will return to this kind of construction a bit later. Uh, well, now I come to the maximal semigroup. I will only state the theorem and give an idea what is the proof. But I want to go later to other things. Hey, I'm sorry. Are you listening to me yet? I am on. Please, yes, I am. I see that I am on. Thank you very much.
Yeah,
It's okay.
So the first point is a refinement of maximality. Well, a semigroup is maximal if it's maximal by inclusion. So if it's not contained in any, is not properly contained in any semigroup. So for to get the results here, I made a refinement and say that a semigroup is f theta maximal if it's maximal with the property of having the flag type of this flag type. Uh, okay, so to get f theta maximal semigroups, we must find subsets in a flag manifold such that the compression semigroup is maximal with this f theta maximality, in this extended generalized sense of maximality. So as I said, the solution is that which are the subsets that make this are the B-convex sets. There is here the precise statement of the theorem that a semigroup S is f theta maximal if and only if it's the compression semigroup of a essentially B-convex set. Start with a B-convex set with non-void interior and take the closure of its interior is a compact set, which is also B-convex, but uh, it cannot be the only subset. This is mainly for technical details in the proof that one must take care. Okay, so the corollary about maximal semigroups is that a semigroup is maximal if and only if it's f theta maximal when f theta is a minimal flag manifold. For instance, in SLN, in the matrix group, the minimal flag manifolds are the Grassmannians. So the f theta maximal semigroups are those that are the maximal semigroups are those that are uh, uh, maximal with flag type a Grassmannian. A Grassmannian. So I wrote here the sketch of the proof if I had time to write down. But this basic, well, in the realm of the semigroup theory, the main point is to the main idea that comes the B-convex set is that there are elements in the group that shrinks the B-convex sets to a point. This is the main point. So if uh, if you start with an open Brouwer cell, then it is the stable manifold of a certain kind of element of the group G. That is, an open Brouwer cell is shrinked to a point by iteration of these regular real elements of the point. Uh, the only proof we exploit is by exploiting this idea. And the fact that the set is contained in open Brouwer cell, we can shrink the set by using this kind of elements and then build the maximal semigroup by taking this kind of elements in the group G. So this is the basic idea is this. The definition of B convexity comes from this basic idea, from this uh, uh, a stable manifold property of the open Brouwer cells. Right. Okay. So I wrote some examples here, but since I came up to here somewhat slowly, I will uh, be a bit faster. That example is that the semigroup of matrices that lives invariant a double cone, not any cone, but a pointed cone, cone that does not contain subspaces and have no-empty interior. Uh, these are maximal semigroups, mainly because the subset that the cone defines in projective space is B-convex in projective space. So these semigroups are maximal, and projective space is a minimal flag manifold. There are some nice examples by change semigroups that live invariant a cone by semigroups that have uh, k by k minors of same sign. This you can look these semigroups as compression semigroups of cones in the exterior product of the vector space. And the same way, the subsets now in Grassmannians are B-convex, and hence the semigroups are maximal with respect to a Grassmannian, and hence maximal. There are another nice example which have been several ways studied by these people of linear algebra, applications of linear algebra, which is the same group of totally positive matrices. That is the same group of such that all minors, here is not exactly totally positive. The terminology here is wrong. All minors have the same sign. This is the sign regular matrices. Totally positive is all minors are positive. These are maximal, but now not absolutely maximal. Maximal with respect to the maximal flag manifold, because the subset it defines is B-convex as well. Recently, I have been thinking about this, an interpretation of B-convex sets in terms of, um, of representations. The point is that flag manifolds can be realized as a projective orbs of the group. The idea starts with the Lie algebra, real Lie. My time is going over. I will be faster. Start with a real Lie algebra, complexify it, and take complex representations of the finite dimensional representations, irreducible finite dimensional representations of the complex Lie algebra. The representation is of real type if its realification is reducible. Then, depending on this can be classified by the highest weight. It's an algebraic theory about this. You can do this theory, and you can realize the flag manifold by as the orbit of the highest weight vector of these in this representation of real type. If you take the dual representation, then you realize the dual flag manifold. There are examples you can build from theory, depending on the highest weight. I put here some Satak diagrams of the real algebras, such that the corresponding highest weight defines a real representations. Here is the Satak diagram for the quaternionic matrices, the SUPQ PQ matrices, and so on for complex matrices. You can look this for the Lie algebra. So for complex, so you can look at the B-convex sets as sets in the product sets in subspaces of the projective space. So you can define the transversality now in vector space. So an element of a projective orbit is transversal to an element in the dual projective orbit, if and only if they are well transversal as with respect in vector spaces. So you have the notion of you can have the Brouwer cells, and you have the notion of duality directly in representation. And you can see that an open Brouwer cell is the intersection of half spaces the same way, and you can characterize the B-convex sets the same way uh, by looking at this. So I came with a problem now. It's quite clear. What are the subsets that comes from convex cones similarly? This is for real vector space. And I am working on this kind of thing, and it seems quite interesting. There will be a talk later about semigroups living invariant convex cone representation. It's related to this problem here, to characterize the B-convex sets that are cones in representations. And there are also this is maybe interesting to get applications like I am finishing applications like characteristic function of semigroups and so on. Okay, and something that I am thinking about is to look at quaternionic type representations and complex type representations, not real type. And so to look also B-convex sets coming from representations this way. And another thing I have been thinking at this moment is a generalization of B-convex sets by BW convex sets, which are subsets can define in the orbits of the product of flags this way. And there is a route to be done here to relate this generalization of B-convex sets to work out this generalization in terms of properties of semigroups. Okay, I will finish here because my time is over. So it's the chair is already nervous about my about time. So thank you very much. I stop here.
Yes, Professor Need, please, you can.
So, I wonder if I understood this statement about the rank 1 groups correctly. Did you say that if you have a B-convex set which is connected, then it is always convex in a Pruha cell in which it is contained?
No, what I said.
Sorry, just a second. Let me ask to somebody with the microphone open. I think that now it's closed. Okay, sorry. No, not yet. I will try to close. Okay.
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 What I said is that in a rank 1 group, the uniflag manifold is a sphere. Yeah. And so any subset, proper subset, is B-convex. admissible because the dual it's complementary subset. It's complementary. I only said about the convex cone. I only said about the projective line, SL2R. So
Okay.
I didn't say, but it seems to be true. If you take well, this class one representation, I never proved this that it comes from a cone. This is the problem I stated at the final very quickly. I stated it only for SL2R. Okay.
Yeah, and I'm asking because I'm thinking about a related question. So if one has a bounded symmetric domain realized in a flag manifold, and then you move it around with an element of the group, and the question is whether the image will remain convex. So typical example is the Riemann sphere. When you take the unit disk, you move it around, then you always get convex sets. But this seems to be hard to prove.
Part of proof, yeah. I don't know. Possibly. What I can say when you have these the semigroups defined in affine symmetric spaces. So it is the compression semigroup of a symmetric space. Well, of an orbit of the affine symmetric. Well, you have the group associated to an affine symmetric space. It's absorbed in certain Grassmannians are in certain flag manifolds are symmetric spaces of the group with a compact isotropy, remain a symmetric space, and this orbit. The semigroup it defines is the compression semigroup of this subset, and these subsets are indeed B-convex sets, and they are B-convex sets. So maybe it's maybe the realization properly may be B-convex sets as well. So it's related to convexity this way.
Okay, thank you.
Okay, I don't know. Just I only have this example in mind.
Okay. Lucas.
Hi, thanks. Martin, what about you when you went to interpretation of the true representations? Actually, before that, is there? I asked myself, is there any interpretation of this stuff? Because you can always think of flag manifolds as boundary of compactifications of symmetric space. So when this kind of invariant sets and so on, I always tend to think of something you're trying to characterize at infinity, like some directions and related to the semigroup, and that you can characterize the semigroup. Is there any interpretation of this theory of convexity related to looking at compactification of the action of the semigroup on the symmetric space, like J over K?
Possibly, as far as I know, no. I don't know, but possibly because what are the open Brouwer cells are the you have this horror cycle. You have one side of the horror cycles and look at the limits of a subset of the horror cycle. I don't know, but.
Because when I was thinking about that in the beginning, and then when you said about using representations, Satake compactifications are built like that. Use representations to build a boundary projective space. Maybe there's something that can shed a light on something.
Yeah. Yeah. I don't know. Well, there is, as far as I know, there isn't anything written about this. So, but I don't know. Maybe you must think this is an interesting problem to be interesting problem to understand these subsets, the flag manifolds, and the boundary properties of symmetric spaces. Right.
Thanks.
So, more questions? I would like to ask some general questions. When we study the flag type of a semigroup, and we can use this concept also to study controllability of bilinear control system. For example, make some mixing of the concept of flag type of a semigroup in variance cone. Then we can apply this to study of controllability of bilinear control system. Then the question is, do you have some idea that we can use the concept of B-Convex to study controllability of bilinear control system?
Well, I wish I had. Well, the problem of controllability is that mainly these properties for semigroups, these properties, as Lucas said, these properties are related to, they are global properties of the semigroups. And the question, the controllability question for control, continuous time control system, the difficulties to relate these global properties with the infinitesimal ones. This is the main point. This is the difficult point. Usually, all this theory of semigroups related to action on flag manifolds, they are of global nature, mainly, well, asymptotical even. And the difficulty is to relate with infinitesimal questions, infinitesimal properties of a semigroup generated by vector fields. This is the invariant vector fields. This is the main difficulty. So, well, well, I have been trying to do this for a long time. Sometimes I get some ideas, sometimes no.
Okay, thank you. More questions, comments? Then, let's thanks to Professor San Martin for your talk. Thank you very much.